Ever feel like we're gonna hit a wall, a digital wall, I mean.
Oh,
Yeah, like with all the photos and videos, the data we're creating, every day there's more.
oh, you're talking about data storage.
Yeah, is there even a limit to how much we can make? It's kind of mind-boggling. And it all comes back to, well, this deep dive's all about binary, that whole ones and zeros thing.
The language of computers.
Exactly. And we're going global this time. We're looking at, get this, a Malaysian computer science textbook. It's called a SAS computer.
Ah, I've seen this one. It's for beginners, right?
Yeah, basic computer form 1, so it gets right to the core concepts. Like, how do you even explain to a computer what a picture is?
It's all about breaking it down, simplifying.
And that's where the ones and zeros come in. Like the textbook says, computers use electrical signals, right? And those signals can either be on or off.
It's like a light switch, the most basic way to represent information.
On or off, one or zero.
Exactly.
They even have this cool illustration in the textbook with light bulbs. Imagine a row of them, and each bulb is like a place value and a binary number.
I like that analogy. Very visual.
Yeah, so if the bulb's on, it's a 1, off is 0. You can have all these different combinations, just like with the ones and zeros.
And that's the beauty of binary. Those combinations create a system that can represent any kind of information.
So it's not just about the ones and zeros themselves, but where they are, right?
Precisely. Just like in our decimal system, the position of a digit determines its value hundreds, tens, ones. In binary, each position represents a power of 2.
Okay, so how about a real-world example? Let's say we have the binary number 1011. How do we figure out what that equals in our normal decimal system?
All right, let's break it down. Starting from the rightmost digit in 1011, we've got a 1 in the ones place, which is 2 to the power of 0, or 1.
Okay, so that's 1, then what?
Next, we have a 1 in the eights place, which is 2 to the power of 3, or 8.
So we have 1 plus 8, that's 9. But what about those zeros in there? Do we just skip them?
Good catch. Those zeros are important, even though they represent off in our light bulb analogy. They still hold a place value. That first 0 to the left of the ones place, that's in the twos place.
So 2 to the power of 1, which is 2.
Right, but since it's a 0, we multiply that 2 by 0, which gives us 0.
So it's like, it's not really the... Okay, and the other 0?
That one's in the fours place. Same idea. 2 to the power of 2 is 4, but then we multiply by 0. So adding it all up, you get...
Let's see, 1 plus 0 plus 8 plus 1, 10. 10, 11 in binary equals 10 in our regular numbers.
Got that.
But can you imagine writing like a whole essay using just ones and zeros? Talk about tedious.
That's where ASCII comes in.
ASCII.
Yeah, it's a code. Basically, it assigns a unique binary sequence to each character.
Yeah.
Every letter, number, punctuation mark.
So when I type an A, my computer's actually getting a secret code in binary.
Exactly. And it's standardized, so every computer speaks the same language. That way, when you send a message, the other computer knows exactly what you meant to say.
That's really cool. Kind of like that movie The Martian, where he uses ASCII to talk to NASA.
Perfect example. It shows how important this is not just for us to read stuff on a screen, but for computers to talk to each other.
From a single letter in a text message to a whole line of code, it's all just secret codes in binary. That's wild. But text is one thing. What about pictures? How do you go from ones and zeros to, I don't know, a picture of a cat meme? So we've got all this text turned into code, but how does that become a picture? Like, what's the connection?
Same idea, really. It's
Yeah.
still about representing information using binary, just in a different way. Remember those light bulbs?
Yeah, each one was like a 1 or a 0.
Now imagine those light bulbs are actually tiny squares on your screen. Pixels.
Oh, right, pixels, the little dots that make up the image.
And just like with the light bulbs, each pixel gets a binary code.
So that's how the computer knows what color to make it.
Exactly. Well, it's a bit more complicated than that. The textbook talks about resolution, dimensions, color depth, those all matter too.
It's like different parts of the code are telling the pixels how to arrange themselves.
Exactly. Take resolution. The textbook calls it pixel density, how many pixels are packed into each inch of the image. More pixels means a sharper image.
Ah, so that's why a 300 dpi image looks so much better than a 72, even if they look the same size at first.
Right. Higher resolution means more pixels, which means more detail. But here's the thing. Every single pixel, even in a black and white image, needs binary.
Really?
Yeah.
Even if it's just black or white?
Yep. Each pixel is either on for black or off for white, a 1 or a 0.
Huh. I never thought of a black and white photo like that. Millions of little lights switching on and off.
Pretty cool, right? And then you've got color depth, which
Yeah.
the textbook shows with those images that get more and more realistic step by step.
Yeah, it's like going from those old 8-bit video games to like a photograph.
Exactly. The more bits you use to define each pixel, the more colors you can have.
So it's like having more crayons in your box. You can make way more colors and shades.
Perfect analogy. But all those extra colors, all that detail, it adds up.
Meaning bigger files.
You got it.
Yeah.
And that's where it gets tricky. We want amazing quality, but we also don't want files so big we can't store them or send them.
It's a balancing act.
Right. And that's where things like file formats and data compression come in.
Yeah.
JPEG, GIF, BMP, those all use binary in different ways.
So like when I save a picture choosing JPEG or PNG, I'm actually choosing how the binary is going to be squished down.
Exactly. Some formats are lossy, meaning they throw out a bit of data to make the file smaller.
That's why my MP3s never sound quite as good as the original song. It's missing stuff.
It is, but it's usually stuff we don't notice as much. It's a trade-off. Smaller file size for little quality loss.
Makes sense. But how does any of this work with sound? Sound's not like a picture, it's not made of pixels.
Yeah, I'm having trouble
Why would-
picturing it. Like an image, you can kind of break it down into those squares, but sound is, well, it's sound. It's like all around.
All about waves, right? Vibrations in the air. So we got to find a way to capture that wave-like nature using our trusty ones and zeros.
So how do you do that?
Imagine the sound wave like a line graph, okay?
Yeah.
It's got those peaks and valleys. What we do is we take measurements at different points along that line.
Like how high up or down the wave is at each point. Exactly. That's the amplitude, the intensity, and we can represent that intensity using binary.
But how many measurements do you even take? Sound is moving so fast, you'd need a ton to capture it, right?
That's where sample rate comes in, kind of like resolution for images. A higher sample rate means more measurements per second.
So a really detailed recording would have a higher sample rate.
Exactly. More detailed, richer sound. It's like the difference between listening to a song on a, I don't know, a staticky old radio versus a really nice speaker system.
Makes sense. So higher sample rate equals better quality. Is that where bit depth comes into, like with the images?
You got it. Same principle. Bit depth for audio, it's about how many bits we use for each of those amplitude measurements. More bits, more detail.
So it's like the higher the bit depth, the more subtle the differences in volume the computer can understand.
Precisely. It's what gives the sound depth and nuance. But of course, more detail, more data, bigger file size, it's always a trade-off.
Back to that balancing act.
Right. And that's where those file formats come in again. Remember how we talked about MP3s using lossy compression? They actually get rid of some of the audio data to make the files smaller.
So that's why my super compressed MP3s sound, I don't know, kind of flat sometimes compared to like a CD.
Exactly. The lossy compression, it throws out some of the less important details, the stuff we don't always notice as much. But if you listen closely,
You can hear the difference. Wow, it's amazing when you really think about it, how much goes into just making sound work on a computer.
it all comes back to binary though. That's the key. All this complexity, all these amazing things we can do with computers, it all boils down to those ones and zeros.
It's kind of mind-blowing when you put it that way, like a secret language that makes the whole digital world work.
And as we create more and more data, understanding that language, that's how we'll keep pushing the boundaries of what's possible. Remember the textbook mentioned the world's largest digital photo?
Yeah, it's huge.
It makes you think, how much data can we actually store? What are the limits?
That's a good question. It's kind of like what we were talking about at the beginning about hitting a digital wall.
Right. And it's a challenge, but it's also exciting. Because as we create more and more data, we have to come up with new ways to store it, to manage it, to make sense of it all.
Definitely. It makes you realize this is just the beginning. There's so much more to explore, so many possibilities with binary.
Exactly. It's not just about the ones and zeros themselves.
Right.
It's what we can do with them, the way they help us connect, communicate, create.
And on that note, we're going to have to wrap up this deep dive. But keep those ones and zeros in mind, folks. They're everywhere. And until next time, keep exploring the fascinating world of how computers see things.